Welcome all of you in this online session. My name is Dr. Vishal Pati. I am working as an associate professor in Department of Mechanical Engineering, Sharad Institute of Technology, College of Engineering, Yadgaon. In today's online session, we will study the fundamental concept related with the availability. It is under the subject of thermodynamics. Then first important point of this availability topic is introduction. The second law of thermodynamics asserts that the energy is degraded during the process. Entropy is generated which reduces capacity to do work. The availability means exergy concept is also derived from second law of thermodynamics and it is closely related with the reversibility and entropy. The availability is the maximum useful work which can be obtained from the system when it operates reversibly at a given state in a given environment. The irreversibility, also called exergy destruction, is waste work potential during a process as a result of irreversibilities. Here we have to develop a availability function and availability balance relation for the closed system and open system. The second law efficiency for various systems is also taken up in this uh, online session in upcoming video lectures. The next important point is source of energy. It becomes clear from the first and second law of thermodynamics that the energy has quantity as well as quality. Therefore, the source of energy can be divided into two categories as high grade energy and low grade energy. Means high grade energies are first one is mechanical work, second one is electrical energy, third one is water power or hydraulic power, fourth one is wind energy, fifth one is tidal energy, and next one is kinetic energy of the jet. The low grade energies are first one is thermal energy, second one is heat obtained from nuclear fission or fusion reactions, next one is heat obtained from combustion of fossil fuels, and last one is geothermal energy. The high grade energy can be converted directly in any form of energy with its equivalent quantity. But low grade energy such as heat cannot be converted directly into high grade energy. The conversion of low grade energy into high grade energy requires a cyclic process and its complete conversion is impossible. According to second law of thermodynamics, the part of low grade energy that can be converted into work is known as available energy and the part which is rejected as a waste is known as unavailable energy. Further, the quantity of energy is always degraded during process, hence entropy is generated and the opportunity to produce work are reduced. The next important point is available and unavailable energy. The quantity of energy is the measure of work potential of given quantity of energy. A reversible heat engine operating between a source temperature Th and sink temperature Tl has a work potential as W reversible net is equals to efficiency of reversible into QH is equals to into bracket 1 minus TL divided by TH bracket complete into QH, where QH is the amount of heat supplied to the reversible heat engine by the source at TH. We can increase the work potential either by increasing the source temperature TH or by lowering the sink temperature TL. However, the lower temperature TL has a large impact on the work potential, but the lowest temperature cannot be below atmospheric temperature T0. Means equation becomes work reversible net is equals to QH into bracket 1 minus T0 divided by TH. The quantity given at the right side of equation is available portion of the total energy quantity QH Therefore, available and unavailable energy can be defined as the available energy is that the portion of the amount of heat energy supplied to the reversible engine which could be converted into useful work. And the maximum work can be also obtained from the reversible heat engine because no any engine is more efficient than reversible engine operating between the same temperature limit. The unavailable energy is that portion of energy which cannot be converted into useful work by any means. The unavailable energy is also present with the total energy. It is low quantity energy and it is upgradation is not possible. For example, the energy in the atmosphere is huge in quantity, but no part of it can be converted into work. Further, all the man-made and natural processes are irreversible, and thus some portion of the available energy is converted into unavailable energy. To overcome the irreversibilities associated with this process, thus increase the unavailable energy of the universe. The next important point is dead state. If the state of the system is brought close to the atmosphere, the opportunity for developing work diminishes and completely when the system reaches thermodynamic equilibrium with the atmosphere. This state of system is called dead state. At dead state, both system and atmosphere possesses energy, but the capacity to do work is zero because there is no possibility of any interaction between system and atmosphere. The property at the dead state are designated with the subscript 0 such as pressure P0, temperature T0 and volume V0 etc. The next important point is useful work. The useful work is defined as the net work done by the system. It does not include the work done on the atmosphere. When the gas expands in a piston cylinder device from an initial volume Vi to final volume Vf, the gas does work W, but all work W would not be able for delivery. A part of this work is used to push atmospheric air at pressure P0 through volume change Vf minus Vi as shown in figure. The work done on atmospheric is equals to W surrounding is equals to P0 into bracket Vf minus Vi, and the difference between the gas work W and surrounding work W surrounding is called useful work. Therefore, W useful is equals to W minus W surrounding is equals to W minus P0 into bracket Vf minus Vi. The next important point is maximum work availability. The work is only produced by the system if it is initially not in dead state. Further, the maximal useful work can be produced if the system approaches the dead state through reversible process. Therefore, we conclude that the system can produce maximum possible work when it undergoes a change of state in a reversible manner from initial state to final state of its surrounding, that is dead state. This useful maximum work is referred as availability of the system. In a simple word, the availability is the useful work potential of the energy content in a system of specific state. Thus, the availability of the system is defined as the maximum useful work that can be obtained from a system when it undergoes a reversible process from initial state to dead state. The availability of the system is sometimes referred as exergy. The next important point is irreversibility. When an actual process occurs, it produces a certain effect. Therefore, the process cannot be reversed and the system and its surrounding cannot be restored to their initial state. During a irreversible process, the total energy remains constant. but the capacity to do work is lost due to the degradation of some portion of the available energy. This degradation of energy is responsible for entropy generation within the system during the process. The entropy generation is always equals to irreversibility involved in the process. Simply, the irreversibility is defined as the difference between reversible work Wmax and actual work W useful during a process. It is designated as I, expressed as I is equals to Wmax minus W useful. Means I is equals to W max minus W useful in kilojoule per kg. The irreversibility generated during process per unit time is called irreversibility rate. I and is given by I is equals to W max minus W useful in kilowatt. For reversible process, W max is always equals to useful work. The W useful, thus irreversibility is zero. The problem based on availability concept. The problem is a heat engine receives heat from a source at 1200 Kelvin at a rate of 500 kilowatts and reject the waste heat to the medium at 300 Kelvin. The process output of the heat engine is 180 kilowatt. Determine the reversible power and irreversibility rate from the process. For this process, for this problem, the solution they have given a heat engine operates between Th is equals to 1200 Kelvin, TL is equals to 300 Kelvin, QH is equals to 500 kilowatt and W useful is equals to 180 kilowatt. To find values are reversible work, irreversibility rate in the process. For the analysis, the reversible work for the Carnot heat engine, the efficiency of Carnot is equals to 1 minus Th upon TL is equals to W reversible is equals to W reversible divided by QH. Therefore, W reversible is equals to 1 minus 300 divided by 1200 into 500 is equals to 375 kilowatt. The irreversibility rate I is equals to reversible power minus useful power. I is equals to 375 kilowatt minus 180 kilowatt is equals to 195 kilowatt. Therefore, QH minus Q reversible W reversible is equals to 500 minus 375 is equals to 125 kilowatt is unavailable energy. The next important point is availability of energy entering a system. The energy may enter the system either as a heat or work crosses its boundary. In actual practice, the heat is added to the system. Its temperature rises from T1 to T2 as shown in figure. If the amount of this heat is directly given to the reversible heat engine instead of system that would produce maximum amount of work. This work denotes amount of heat as available energy. The available portion of heat energy that crosses the boundary of the system may be determined by assuming that reversible engine receives the heat in the same manner as the system receives. Consider a differential amount of heat delta QH is added at the temperature T at to the reversible heat engine. Thus, the reversible engine operates between the temperature level T and the temperature of the ambient T0. The maximum work produced by the engine become available portion of delta QH is given by therefore delta W max is equal to delta QH into bracket T minus T0 divided by T. The unavailable portion is equal to delta QH minus delta QH into bracket in numerator T minus T0 divided by T is equal to delta QH into T0 divided by T. The hatched portion in the figure represents the unavailable portion of the energy added. Unavailable energy added is equal to T0 integration 1 to 2 delta Q divided by T. Therefore, delta Q divided by T is equal to ds. The unavailable energy is equal to T0 into bracket S2 minus S1. The available portion of energy added is equal to QH minus T0 into bracket S2 minus S1. Since the final temperature difference must be added to cause the heat flow from body to another, but the heat flow from the high temperature source to the relative low temperature body, the temperature of heat energy decreases source to destination, thus the capacity producing work is lost. As per the figure, the loss of available energy during heat transfer, the source transfer of heat energy irreversibly, its temperature decreases from T1 to T2 as a result of heat addition to the system. Its temperature increases from T3 to T4. The average temperature of heat transfer to system is less than the average temperature of heat addition from the source, thus the available energy is reduced during such heat transfer processes. The availability aspects. The availability is a measure of work potential of system that system can deliver when it brought to atmospheric conditions. The second point is the value of availability cannot be negative if the system is at any state other than the dead state. The system would be able to change its conditions spontaneously towards the dead state, and this tendency is completely caused when the system reaches dead state. According to zero work is being developed and thus available at maximum work cannot be negative. The availability is third point is the availability is not conserved but is destroyed by irreversibility as limiting case as the availability of system may be destroyed completely if there is no provision obtained the work. Fourth important point is the availability is thus viewed as a maximum theoretical work obtained when a system passes a given state to the dead state while interacting with the atmosphere only. And fifth important point is the availability is an extensive property. The next problem based on availability is air at 1 bar and 27 degrees Celsius is heated in a non-flow system at a constant pressure to 177 degrees Celsius. The heat is supplied from constant temperature reservoir at 577 degrees Celsius. The atmospheric temperature is 20 degrees Celsius. What percentage of heat added per kg of air is available energy? For this problem, they have given P is equals to 1 bar, T1 is equals to 27 degrees Celsius, T2 is equals to 177 degrees Celsius, pH is equals to 577 degrees Celsius means 850 Kelvin, T0 is equals to 20 degrees Celsius means 293 Kelvin. To find value is the percentage available of energy of heat supply. For this problem, assumption is the specific heat of air at constant pressure is 1.005 kilojoule per kg Kelvin. For the analysis, the heat transfer to air at constant pressure QH is equals to Cp into bracket T2 minus T1 is equals to 1.005 into bracket 177 minus 27 is equals to 150.75 kilojoule per kg. The unavailable energy Q unavailable is equals to QH into T0 divided by TH means 150.75 into 293 divided by 850 is equals to 51.96 kilojoule per kg. Therefore, the available energy A is equals to QH minus Q unavailable is equals to 150.75 minus 51.96 is equals to 98.8 kilojoule per kg. The percentage of heat added available energy is equal to A divided by QH into 100, means 98.8 into 100 divided by 150.75, means 65.53%.